Now, let's welcome our last semi-preliminary speaker, who is Binoy Krishna Hazra. He obtained a PhD in experimental condensed material physics in 2018, and after that, he was a postdoc under the Prof. Stuart Parkin at the Max Planck Institute, and now he's the assistant professor in physics department at IIT Guwahati, India. And his research focused on the spintronics device based on intermetallic and oxide thin film, and especially the studies on magnetic non-collinear antiferromagnet. So now let's welcome him for the last semi-plenary talk.
Yeah, thank you, Dr. Hang. Am I audible properly?
Yeah, I can see, and everything is fine.
Okay, thank you for the brief introduction, and I would like to thank the organizing committee as well for giving me this opportunity to present our work. So today I will talk about seeded spin orbit torque in non-collinear antiferromagnet. And this is the outline of my talk. So I'll start with antiferromagnetic spintronics and why non-collinear antiferromagnet. What is the importance of these non-collinear antiferromagnets? And then I'll discuss a current-induced switching, magnetization switching basically. And then in detail, I'll discuss the switching mechanism, and then I'll summarize the result. So in spintronics, where electron spin and charge both are utilized, which gives an additional degree of freedom compared to the charge-based conventional electronics. So there are various spintronic devices, and few of them are already commercialized. So most well-known devices are GMR devices, giant magnetoresistance devices, where two magnetic layers are separated by a non-magnetic layer. And another device is called magnetic random access memory, MRAM, where two magnetic layers are separated by an insulating tunnel layer. And depending upon the resistance, whether it's high or low, it will act as a 0 or 1. So till today, we broadly use ferromagnet for these spintronic devices. So the main reason is in ferromagnet, there is finite net moment, and it's easy to manipulate the magnetization or domain structure by external magnetic field and or external current. And the writing or reading speed in this class of material is typically in the gigahertz range. But because of this small magnetic or because of this finite net moment, there will be a finite stray field always, and that limits the data density in a device. In contrast, an collinear antiferromagnet, where the net moment is 0, so there the data density can be enhanced tremendously because there is no stray field as there is no net moment. But it's difficult to manipulate the magnetic structure or magnetization by external field or external current. But at the same time, in collinear antiferromagnet, the magnetization dynamics is in terahertz region. So the writing and reading speed will be very fast. Also, there is another class of material is called non-collinear antiferromagnet. Suppose you have two spin, let's say red and this blue, they are antiparallel, and you bring another spin. So then there will be a frustration in this system, and this third spin can be up or down. And then the result spin texture will form a triangular lattice. And in this kind of system, the net moment will be nearly 0 or 0. Depending upon the situation. So in terms of magnetization, it behaves as a collinear antiferromagnet. But in this kind of system, because of this non-collinear spin configuration, it generates finite Berry phase, which gives rise exotic magnetotransfer properties like large anomalous Hall effect, magneto-optical Kerr effect, large Nernst effect, similar to the ferromagnet. So it's a combination of ferromagnet and collinear antiferromagnet. One can think that way. So in terms of magnetization, it behaves as a collinear antiferromagnet, whereas in terms of properties, it behaves as a ferromagnet. But there is a clear, one can distinguish this ferromagnet and non-collinear antiferromagnet clearly. The anomalous Hall effect, let's say. So usually in ferromagnet, it scales with the magnetization, whereas in non-collinear antiferromagnet, it doesn't scale with the magnetization, as the magnetization is nearly zero and the origin is different. So in right now, the existing problem is ferromagnet and non-collinear, ferromagnet and collinear antiferromagnet. And now let's see how non-collinear antiferromagnet can be useful to solve this problem. So among various non-collinear antiferromagnet, in particular intermetallic system, the first report was on manganese-3 tin single crystal by a Japanese group, Nakasuji et al. So they first time they observed large anomalous Hall effect in manganese-3 tin crystal, and that large anomalous Hall effect was not related to the magnetization, and the magnetization was negligibly small. And at the similar time, Naik et al. Also observed a large anomalous Hall effect in a sister compound, manganese-3 germanium. So since this compound shows a large anomalous Hall effect, so the open question was at that time whether it's possible to manipulate the magnetization or domain structure or not. So with this motivation, we started the work. So we have taken the manganese-3 tin as a model system. So this is a typical spin texture you can see. So here, manganese-3 tin basically crystallizes in hexagonal crystal structure, and manganese spin form the triangular lattice. So the Heisenberg exchange interaction and Zalewski-Moria interaction favors for 120-degree antiferromagnetic ordering. So when it is perfectly 120 degrees, so the net moment is exactly zero. But due to the presence of small in-plane anisotropy, this breaks this 120 antiferromagnetic ordering, and the moment, the manganese spin tilt little bit, and then it generates finite net moment. And this tiny moment basically control the domain structure of this manganese-3 tin compound. And it shows exotic magnetotransfer properties like anomalous Hall effect, anomalous Nernst effect, magneto-optical Kerr effect, due to this controlling this domain structure by the small in-plane moment. So it has 6 degenerate domain structure, 30 degree. So these are denoted as how the manganese spins are oriented, and the green arrow basically shows the net moment of this triangular system. So there are 6 degenerate ground state: 30, 90, 150, 210, 270, and 330. And these are the high energy domain configuration. So we have prepared manganese-3 tin sample with the thickness range 30 to 100 nanometer on sapphire substrate, where the Kagome plane was perpendicular to the film plane. And on top of that, we have deposited tungsten, 8 nanometer tungsten layer, which acts as a spin current generating layer. And the entire structure was capped with tantalum nitride to prevent the oxidation. So typically X-ray diffraction shows that the manganese-3 tin oriented 112 bar, 0 direction. So textured along this direction, it's not fully epitaxial. And further STM image shows the manganese-3 tin is locally highly ordered, and the Kagome plane can be seen clearly. Further, we have performed the magnetization measurement, and the red curve shows the raw data, and one can see the diametric contribution of the substrate dominates in this raw data. And when we correct the diametric background and we observe this blue curve, so this is a small moment presence in this along the Kagome plane. So then the entire structure was fabricated into a hall bar as shown here, and we apply a small DC current, 1 milliampere along the X direction, and sweep the outer plane magnetic field that is along Z direction, and measure the transverse voltage, which is nothing but anomalous Hall resistivity. And what we observe? We observe a large hysteresis. The coercivity is around 1 Tesla. And the magnitude of Hall resistance from, let's say, from top to bottom is nearly 100 milliohm. And among these 6 domains here, 90 and 270 degree domains are in the case of magnetic field induced switching. 90-degree and 270-degree domains are responsible as the net moment, which is shown in green arrow, that is along Z or minus Z direction. Then we perform the current-induced switching experiment. So in this current-induced switching experiment, the charge current is passed through this bilayer, and tungsten layer basically generates spin current due to spin-Hall effect, and that spin current propagates to the proximal layer, and that proximal layer is here manganese 13 and applies a torque on the net moment of the manganese 13. So here we use two protocols, and in this presentation I will discuss only one protocol. So in this protocol, we apply 100 millisecond writing pulse and then wait for a few seconds, like 0.5 second, and then we apply a small read current, 1 milliampere, and then measure the time first resistance. And what we observe, a deterministic switching in the presence of bias field. So the bias field is Hx, which is along the x direction. So when the bias field is positive, we can see that this is the blue curve. And then when we reverse the bias field, the polarity also changes. So this is typically observed in spin orbit torque induced magnetization switching. And here one can see the switching magnitude. The change in the Hall resistance is nearly 40 milliohm. So if you calculate the switching percentage, so that is on only 40%. So the reason is here 90 and 270-degree domains are not playing any role. The other four domains, like 30-degree, 150-degree, 210, and 330, those four domains are playing role. So the domain is switches, let's say, from 30 to 210 or 150 to 330. And one can see if you take the projection of this green moment along the Z or minus Z direction, so that should be 50%. The switching percentage should be 50%. So that has been calculated theoretically. And we observe 40%, which is close to the theoretical value. Note that when the bias field is 0, we don't observe any current-induced switching. The switching was 0. So this profile shows the current-induced switching as a function of bias field. So we apply different bias field started from 50 oersted. So when the bias field is small, then current-induced the switching magnitude or the change in the Hall resistance is small. As we increase the bias field, the switching magnitude increases, and then beyond 0.1 Tesla, the switching magnitude decreases, all the Hall resistance decreases. And from here, we extracted the current density and the Hall change in the Hall resistance and plotted here. So the current density shows a independent behavior as a function of, it's independent as a function of with respect to the bias field, whereas the change in the Hall resistance shows a non-monotonic behavior. So initially it increases, it maximum, and then again it decreases. So let's compare this profile with the standard ferromagnet, where spin orbit torque induced switching has been observed in various studies. So we have taken tantalum coffee B MgO structure, and we perform the current induced switching, and we extracted the current density and the switching magnitude. And what we observe, the current density, typically this is observed in various studies as well. So the current density, it strongly depends on the bias field, whereas the switching magnitude almost independent of the bias field. So if you call this standard ferromagnet like coffee B switching is because of the spin orbit torque, then the manganese 13 switching is beyond spin orbit torque. So there is spin orbit torque, but there is not conventional spin orbit torque. So to understand this switching mechanism in detail, we perform more experiment. Here we perform the pulse width dependence switching experiment. So previously, whatever I showed, that was for a fixed pulse width. So that was 100 millisecond writing pulse. So now we have changes. We have varied the pulse width from millisecond to nanosecond. So when the pulse width is large, like let's say millisecond or microsecond, we observe the switching percentage is large. It's almost constant, and it's 40%. And when we perform the switching at low pulse width, like nanosecond pulse, like 100 nanosecond, and then we observe the switching magnitude reduced drastically. So based on this, we propose the switching mechanism, which can be understood from this cartoon. So, so this blue curve is basically the writing pulse profile. So initially the writing pulse was off, and then it was on, and then it off. So this is the fall time. And this cartoon shows basically a typical a representative figure of manganese 3 domain structure. So here 30 and 150 domains are equally populated. So 30 is this one, and 150 is this one. So these two domains are, let's say, equally populated, and the bottom layer is basically tungsten layer. So when writing pulse is off or writing current is off, so this is equally populated, and then as soon as we switch on the write pulse, so then the tungsten layer basically generate some spin current, and then so that spin current basically propagate, or it switches the interfacial layer close to the tungsten, few layer of manganese 13, and which is here, it's shown here in gray color. So here the domain structure is 0 or 180. So initially it was 30 or 150. So so these are low energy state, and then from here it goes to 0 degree or 180. So these are high energy state. So the complete switching will happen when it cross 180, and this is barrier, and then reaches to 210. Okay. So when the writing pulse is off, so there is some small switching happen close to the interface, and it form a small layer, which is we denote as lambda s, and this is basically we call it as seed layer, and the remaining layer, which is shown in red color, where all domain configuration is possible. Now the remaining layer can be switched or not, so that depends on how you switch up the write pulse. So if you switch up the write pulse slowly, then system will get enough time. Then the entire layer, entire thickness or entire layer will be switched, and then it will relax into 210 or 210 or from 330, 210 or 330. So now in the case of millisecond pulse, what happened? In the case of millisecond pulse, the typical fall time is greater than 50 nanosecond. So the system gets enough time, and then or the system pulls in the presence of the spin current, and that's why it relaxed to 210 or 330 domain structure. And then we observe maximum switching percentage, that is 40%. In the nanosecond case, one can see the pulse fall time. It is very fast. It's order of 750 picosecond. And in that case, system pulls in the absence of spin current. Because of this sharp drop, the fall time is very fast. So the system pulls in the absence of spin current. So that's why the full switching doesn't happen, and we observe only partial switching. So that's why the switching percentage is less than 10%. And if you go further low pulse width, the switching will be very small. Also, we have performed another experiment in the nanosecond pulse. When we apply a additional current, additional DC bias, and then we observe the switching percentage increases. So from this experiment also we can tell heat plays a role in this switching experiment. So also, so far I discussed one protocol where we apply a 100 millisecond writing pulse, and then we wait for 0.5 millisecond, and then we apply a small read current to measure the transverse resistance, and we calculate the switching percentage. So now we perform another type of experiment where writing and reading was done at the same time. So we apply writing pulse, and then measure the read, we apply the read, and then measure the transverse resistance. And then this is the data for difference bias field. So at zero field, there is no switching, that is the black curve. And then when bias field is finite, we observe some switching. But the switching behavior is the switching graph looks completely different compared to the earlier, which is case one, where there was a delay. And when we correct from the zero field, and we see here as well, nearly 40% switching for 0.1 Tesla. So that, and also theoretically it has been calculated. We observe similar profile and it matches quite well. So only the difference is experimentally the current density is 10 to the power 11 ampere per meter square, whereas theoretically we need 10 to the power 14 ampere per meter square. So from this we can see also heat plays a role in the current induced switching experiment. And it can be explained using conventional spin orbit torque. And another most important observation from this experiment, what we observed, we performed the switching experiment for different temperature. So 250, 350, 300, and 380. So as expected, as we are approaching to the nil temperature of this system, so nil temperature of this system is 420 Kelvin. So the current density decreases. But the Rx value, one can see it remains same for this all temperature. So whether it's 250, 350, 300, or 380, the switching happen at particular Rx. So this Rx, particular Rx is basically tells that the system heats up to certain temperature, which is corresponds to this fixed Rxy value, and then switching happen. Whether it's 250 or 380, doesn't matter. So the system reaches, let's say 450, and then it cools. So this fixed RS basically tells the switching is basically again heat assistant. So in summary, we observe a deterministic current induced switching, and heat plays a crucial role. And we could switch a 100 nanometer thick layer. So that is the beyond the its spin diffusion length of manganese 3 tin. So typically spin diffusion length is 1 or 2 nanometer in the case of manganese 3 tin. So that can't be explained using the standard spin orbit torque model, whereas our seeded spin orbit torque is can explain our result quite well. And this was a teamwork, and so I'd like to thank all of my collaborators as well as co-worker like Bonavir Pal and Chechun and Borge, and obviously Sihun and Stuart and Ingrid. With this, I'd like to thank you all for your kind attention, and I'd be happy to answer if you have any queries or questions.
Okay, thanks, Dr. Binoy, for the very inspiring and exciting speech. So now it's a Q&A session. Please raise your hand, just directly unmute yourself and ask. If no, I actually have some questions to ask,
Yeah,
Doctor.
please.
Yeah, I want to ask about the deposition method of your manganese treating. So is it
Yes.
by sputtering or MB?
Yeah, it was by sputtering. So we use post sputter. So we have taken manganese one target, and then tin one target, and we post sputter, and then yeah. So deposition was done around temperature. So we deposited at 200 and then annealed at 350 degree.
So you are nearly in situ in the deposition chamber. Okay.
Yes.
So and also the from the XRD result, it looks like polycrystalline.
Yeah, it's
property, right?
polycrystalline. Yeah, exactly. It's polycrystalline. But when we did some texture analysis, and from there we found 112 bar. It's textured along 112 bar. It's not like fully polycrystalline.
Okay. I have another question. So in the current induced switching measurement, you were talking about mainly the 30-degree, 120-degree, those domains contribute.
Yes.
I wonder what happened to the 90 and the 270. These domains, what are they doing during the current induced switch?
Yeah, so these domains. So this domain, if you look the torque from this domain, so there will be no contribution from this domain, and that's why in this 90 or 270, it doesn't contribute to the current induced switching. In later, I think Nakasuji group and other group also, they have induced some uniaxial strain in the system, and then they stabilize one type of domain. Let's say it's either 90 or some other domain, and then they observe full switching as well.
I see. Okay.
So here
So
it was 6 domain, and
yeah.
they plays different role in the case of field induced switching and current induced switching. But if you have a one type of domain, so then that will contribute in both.
Okay. And
Excuse me, sir. Sir, I had a query.
Yeah.
Yeah, I wanted to know, sir, is this tungsten is like alpha tungsten phase or it's beta tungsten phase?
Again, it's a mixed phase, I will say,
Okay.
because the manganese 13 itself, it's a polycrystalline, it's a
Right.
textured sample. So on top of tungsten, we could not grow beta tungsten.
Yeah, because I was wondering if it could have been beta tungsten with higher spin Hall angle. It could have been like
so here the higher spinol effect material is not important. So here the important is how you stabilize the manganese 13 domain. So if you can stabilize with one type of domain, let's say 90 or 270, then you will see full switching. But here we could stabilize all the domain because of this our polycrystalline nature. So that's why we see less switching or 40% switching.
Okay, thank you, sir.
Yeah.
okay, and there is one question typed in the chat. Can you briefly explain the difference between magnetization and non-magnetization scaling in AHE?
Let me read. Can you briefly explain difference between magnetization and non-magnetization scaling? So typically in the anomalous Hall effect, the ordinary Hall effect, if you look, so it is proportional to the external magnetic field, which is observed in typical non-magnetic metal. And when you have a spontaneous magnetization, let's say iron, nickel, cobalt, or any ferromagnet, then there will be additional contribution in the transverse resistance. So that will be, let's say, external magnetic field plus your spontaneous magnetization contribution. So that's why you can see if magnetization is more, then your Hall resistivity will be more. So that is typically in the case of ferromagnetic material. Whereas in non-magnetic material, non-magnetization, if you think it's non-magnetic material like copper or other, so there will be only ordinary Hall effect. But there are some material like non-collinear antiferromagnet, so their moment is very small. So it is like 10 to the power -3 or typically mu b order. So then, and then we observe, let's say, or large anomalous Hall effect. So then you will see there is no correlation between the magnetization and anomalous Hall effect and magnetization. You can't correlate. So if you compare, let's say, iron, that magnetization, the let's say 1000 TMU per cc is corresponds to this amount anomalous Hall effect. So if you do similar comparison with this non-collinear antiferromagnet, so that will be not satisfied. So that's why it doesn't scale basically.
Does it answer your question? Okay, we have two other questions from one. Okay, yeah, it answered.
Does the thickness of the manganese play a role in? See, so in this thickness range, we don't see any role. So we have we measured for different thickness. I didn't show here, like 30 nanometer, 40 nanometer, 60 nanometer, 80, 100. So 30 to 100 nanometer, we always observe 40% switching. So that is summarized in our supplementary data in this paper. So, so it doesn't matter. It is independent of thickness, actually, the switching magnitude.
And okay, there is another one. Yeah.
Yeah, maybe just following my question.
Yeah,
sorry.
So,
yes. Continue. Okay.
Yeah.
Yeah, just wondering, like, because you are the sample is the polycrystalline, like you have different thickness. I just wondering, like, does the thickness, like the Kalkumet plane, is consistent through the thickness, or because just your sample is polycrystalline, you cannot have you will not have this problem if this is not consistent through the thickness.
Yeah. So so whether it's consistent or not, it's difficult to answer throughout the thickness. But from X-ray, at least for all the sample, we observe that it is textured along 112 bar orientation. That is one thing. And when we perform the tunneling electron microscopy, like and from that experiment, we observe the locally it's very ordered sample, although it looks polycrystalline. And from TM, what I showed that it looks quite ordered structure, but globally it's a textured sample.
Okay, thanks.
So another question is, out of 6 domain state, on which basis you are saying 90 and 270 is responsible, and rest 4 is so the basic understanding is, let's say we apply, so the Kagome plane is here perpendicular, right? So the in-plane moment usually lies in the Kagome plane. So the moment, the small in-plane moment is along the z-axis. So if you look at all the domain structures, the 6 domain structure, 30, 90, 150, 210, 270, 330, among these, the green color, the small green color arrow, basically represent the net moment in each domain structure. So here only 90 and 270 is along the z-axis or z-axis, basically plus minus z-axis. So when we apply the external magnetic field, so there the maximum switching, field-induced switching happen because of this 90 and 270. So that is a reference point you can think. So here we observe 100 milliohm, and with respect to that, in the current induced switching experiment, we observed ideally, so the remaining domain, if you look, so they are at an angle with respect to z-axis, and if you take the projection, so that will be 0.5 times m. So the theoretically you can find 50% switching happen between 30 to 210 domain structure or 150 to 330 domain structure. And that's what that this 4 domain is contributing to the current induced experiment, and we observed a less switching, like 40% switching. Is it clear?
Okay. He said yes, thank you.
Yeah.
Does anyone else have question? Okay,
thank you.
If no other question, then let's thank again Dr. Binoy for giving a very inspiring talk. And yeah, and we learned a lot. So